Okay, now that we have talked about how we calculate an intercept and a slope, how we use this basic equation, where we say y is equal to, we have it as the equation right in the very top one here, y is equal to an intercept plus a slope times x plus air, and we can calculate a intercept and a slope to minimize the sum of the squared air. And we get a slope that tells us the expected increase in y given a 1 using increase in x, and our intercept tells us what is the expected y when x equals 0. And now I have our equation we've been looking at the top here, and I've written 2 more equations. And I have some questions down at the bottom of this page. It should look very familiar to you because we've been seeing these same questions over and over and over again. And we're going to follow the same pattern. Identify which of the equations above is an equation for variance in a sample. What are equations for sampling air variance in a population? And for the equation that's for variance in a sample, within that equation will include variables and parameter estimates, and what are the variables and what are the parameter estimates. And see if you can answer all those questions before I tell you the answers, because we're going to follow the same pattern we've followed in previous units. It'll be the exact same process. And if you apply the reasoning from previous units here, you should get the same answers. So first, what is the equation for variance in a sample? That's the one we've been looking at. This very top equation right up here is the equation for variance in a sample. It tells us we have, here's our sample right here. We've got different people, and they have different scores on y. And so we've got variance on y, and this is the equation helping us understand that variance, in this case, variance in anxiety ratings among people in our sample. So the top equation is looking for variance in a sample. And in that top equation, we have variables and parameter estimate. What in that top equation is a variable? Note that I've added the subscripts here. So I say y for individual I in sample S is equal to the intercept for sample S plus the slope for sample X times the score in X for individual I in sample S plus the error for individual I in sample S. So in that equation, what are the variables? So the variables is everything with an I in the subscript, things that can vary from one person to the next. So every person has a different score on anxiety rating, or they can have a different score on anxiety rating. Everyone can have a different score on X, number of traumatic bunny incidents, and everyone can have a different error. The difference between their observed and predicted value can differ for every person. So the Y, X, and E all have subscripts I and S to designate it's for an individual in our sample. So Y, X, and E are our 3 variables. And then if those are the 3 variables, what are the parameter estimates? So the parameter estimates are the intercept and the slope, beta naught and beta 1. And note that there's just one parameter estimate for the entire sample. Based on our entire sample, we calculate a single intercept and we calculate a single slope. So there's only one intercept and one slope based on our entire sample. And then, as before, every parameter estimate that we estimate in our sample becomes an outcome for our equation for sampling air variance in a population. That is, we estimate a parameter, and then we say in the population, how much is our study, the parameter estimate from our study, how much does that parameter estimate deviate from the true population parameter? So we have, here's the parameter estimate of the intercept in our study. The intercept for sample S for population P is equal to the true parameter, I'll do that Greek beta, the true parameter for the intercept in the entire population, plus the error, how far the parameter estimate from our sample deviated from that true population parameter. And likewise, I'll do the exact same thing for our slope. Beta 1, that's our slope. Our slope, our parameter estimate for the slope that we got from our study, our parameter estimate, is equal to the true population parameter plus the error, how much mistake we made, how much our study deviated from that true population parameter. So the beta, the slope for study S from population P, is equal to the true population parameter for population P plus the error, how much study S deviated from the population parameter for population P. And so we have the same two types of equations for variance in a sample, equations for sampling error variance in a population, and in our top equation for variance within a sample has variables and parameter estimates, and every parameter estimate in our top equation is taken out and comes down here, has its equation of its own, where we predict that parameter estimate and say that parameter estimate is equal to the true population parameter plus error. And as we've done before, we're going to take these equations and consider two basic types of questions we can address. The descriptive question, where we want to describe effect sizes and answer the basic question we're trying to address in research. In this case, what is the association between X and Y? What's the relationship between number of traumatic bunny incidents and anxiety ratings? So I want to answer that descriptive question. And then the inferential question is, when we do our study, how close do our parameter estimates come to the true population parameter? How good do our results generalize to the larger population? Did our study produce a result that was just a random fluke and unusual and doesn't represent the population at all? Or does our study give us information that's a pretty good descriptor of what the population is really like? That's the inferential question. And we're going to look at the same types of things to answer those questions. So the descriptive question is we can answer that with our parameter estimates. So we have our intercept and our slope, and those two parameter estimates can be used to address the descriptive question of what's the relationship between X and Y. How strong of a relationship is there? Now, this is kind of the same thing we had in our previous unit, where we had a parameter estimate which was the mean for group 0, and another parameter estimate which was the difference between two means. And we wanted to know the difference between two means and really didn't care about the specific mean for group 0. And we have the same thing here, where we've got a parameter estimate that's a intercept, and we really don't care about that. It's not interesting. It's not something that's part of our study. We don't, if we want to know what's the relationship between traumatic bunny incidents and anxiety rating, we don't really care what the anxiety is when bunny incidence equals 0. That's not really part of our research question. It's something we need that in our equation for everything to work, but it's not a key research question we're trying to figure out. So our intercept is something we usually don't care about. We can talk about what that is, but it's not part of why we're doing our study. What we really care about, what we really want to know the descriptive statistic for, what we really want to know the effect size for, is our slope. That slope tells us the strength of relationship between X and Y, and that's what we really care about. So our slope, beta 1, will answer that descriptive question. Now, we could go on and talk about inferential statistics, but before I do that, I want to kind of go down a whole other path for a while here and talk about some other ways we could describe the effect size here. Now, the slope will describe an effect size, and it does just fine at that. So why do we need other ways to talk about our effect size? What's going to happen here is I'm going to talk about some other ways to describe an effect size that will be more flexible than just the slope by itself. This gets back to the difference between a focused question and an omnibus question. Looking at a focused question, where I just want to know what's the relationship between two variables, say, how often do you wash your hands and what's your level of health? I just want to know, are those two things related? Then a slope does just fine at that. But if I have an omnibus question where I want to say, how much is health predicted by how often you wash your hands, and maybe also how much sleep you're getting and how much you're exercising. If I want to take those three things and try to predict someone's health, and say overall, how much variance am I explaining in health given those three predictors, that's beyond what I can address with just two hands. That's an omnibus question. And beta weights aren't really going to be able to handle that very well for us. So to set us up for answering those questions, some omnibus questions, larger questions, we need some other ways of understanding effect sizes. For this unit, I'm going to look at some other ways of talking about effect sizes, and they're essentially all going to do the same thing. We can look at betas, or we can look at about these other ways I'm about to describe. No matter how we do it, we're going to come to the same basic answer about the relationship between X and Y. So at the moment, it's going to be a redundant way of looking at effect size. But in future units, each of these approaches is going to give us something different and will be useful to us in different ways. So let's look at another way Here I have another way to describe the effect. So we haven't taught, so in our previous units, we've looked at the errors for how far our sample statistic, our sample parameter estimate deviates from the true population parameter. And we call that, see if you can recall, what do we call that? If I say, what on average, what's the average size of these E's? The average size of how far our statistic typically deviates from the true population parameter is called what? The average size of how far our E's typically deviate from the true population parameter is the standard error of the statistic that we're looking at. As we'll see later, this is for a beta, and so the average size of these E's is going to be the standard error of our beta. But I'm jumping ahead of myself. I'm going to talk about that later. What I want to do now is talk about the E's for our top equation. We actually haven't been talking about those recently, but let's take a look at that. What is the average deviation of those E's? So this is the EIS, how far the predicted score, or how far the observed score for individual I in sample S, how far that person's observed score deviates from his or her predicted score. How far does observed deviate from predicted? And so the average size of those E's is how far on average the observed deviates from the predicted score. That's the average amount of mistake we make if I'm trying to use my equation to predict people's scores. Now, can you tell me, can you think about what do we call that? If you go back to that Google Edge sheep table, in fact, actually that Google Edge sheep table, we talked both about what is the average size of the E's for how far parameter estimates deviate from true population parameters, how far statistics deviate from true population parameters. And we talked about these E's up here. We talked about how far predicted values typically deviate from observed, or how far observed deviate from predicted values on average. So we've talked about both of these types of E's, and we've talked about the average deviations for both types, and they had two different names. So what is the average deviation of these E's? If you recall, this is the standard error of estimate. Tells us that the average deviation of the absolute values of the E's in the top equation, EIS, how far individuals deviate from their predicted values, that is the standard error of estimate. So what this shows you is that the standard error of estimate is actually another way to describe the effect. It's an inverse association. As the beta gets bigger, that means a bigger effect. As the standard error of estimate gets bigger, that means it's a smaller effect. So the standard error of estimate is inversely related to your effect size. As your effect size gets bigger, your errors get smaller. That is, your standard error of estimate gets smaller. Let's take a closer look and see what that standard error of estimate is. So here I've taken our same example, and I have everybody's score on traumatic bunny incidents and a score of anxiety, and I'm looking at how far each person's predicted value deviates, or how far each person's predicted value deviates from their observed. So this person was 13 points below. I forget who that was. Was that Cal or Gus or somebody? Was 13 points below what we predicted. This person was 4.5 points below. This person was 4.5 points above what we predicted. And so I'm just looking at each person's error, how far their observed deviated from predicted. That is y minus y hat, observed minus predicted for each person. And as it turns out, if you sum all these errors and you keep the negative signs, the sum of these errors will always equal 0. Just like when we calculated deviations from a mean, when we calculated the standard deviation and looked at how far people's scores deviated from the mean and calculated everyone's deviation score and kept the negative signs, the sum of the deviations around the mean always summed to 0. The same exact thing happens here. The sum of the errors, how far people deviate from the regression slope, how far people deviate from this red line, the sum of those errors will always sum to 0. Now, we're going to do the same thing we've done elsewhere, where I'm going to take those deviations and square them. So I take each person's deviation and square it, and then I'm going to add it up to get the sum of the squared errors. In this case, I sum all those, I take each error, square it, sum of it, I get a sum of squares of 380. And note, this is the thing that was minimized when we calculated our regression equation, and we calculated our intercept and the slope. and we calculated our intercept, which was the covariance divided by the variance of x. When we calculated all those things and plugged in our equation here, the equation minimized the sum of the squared errors. That was that t-shirt I mentioned back there, the minimize this t-shirt, minimize the sum of the squared error. This right here, 380, that is the sum of the squared error. That is a thing that is minimized when we calculate, there we go. That is a thing that is minimized when we calculate our regression equation, when we calculate our intercept and our slope. So this is our sum of our squared errors, 380. And this sum of the squared errors is a thing that's going to be a larger value when there's a lack of relationship between x and y. And as the relationship between x and y gets stronger, this is going to get, the sum of squared errors is going to get smaller and smaller. So the sum of squared errors is a value that gets bigger as your mistake gets bigger, that is, as the effect gets smaller. And as the effect gets bigger, as there's a stronger relationship between x and y, then your sum of squared errors gets smaller. Now let's look at how we would calculate the standard error of estimate and see how that compares to a standard deviation. They're very, very, very similar formulas. Now, previously, when I gave you the formula for a standard deviation, I used an x rather than y, but we can use an x or y. And because with regression, we always use x to predict y, y is the thing that's getting predicted. And because y is getting predicted, we always frame our question in the way of we're trying to use x to explain variance in y. So we want to know how much variance there is in y. So when we're trying to predict things, we're talking about how much mistake do we make when we're predicting y. So y is our target. So just to make things comparable, rather than using x's, I've used y's for my standard deviation over here. So for standard deviation, I could say x minus x bar squared. Here I've got y minus y bar squared. That's our sum of squares. And note how the sum of squares for standard deviation is how far people deviate from y bar, the mean. Standard error of estimate is almost the same thing. The only thing, instead of a bar, I have a hat. Just switch out that bar for a hat, and rather than how far each person deviates from the mean, I have how far each person deviates from their predicted score. Observed minus predicted. So for standard deviation, we had observed minus the mean. Standard error of estimate, we have observed minus predicted. And so with standard deviation, this first step, we call this the sum of the squares. And for the standard error of estimate, we'll call this, if we take observed minus predicted and square it and sum it up for everybody, we'll call this the sum of the squared error. That's what we were just looking at on this previous slide right here, 380. That's our sum of squared error. And that's our first step. And then we're going to divide by our degrees of freedom. So for our standard deviation, we call this the variance, which is the sum of the squares divided by our degrees of freedom, which was n minus 1. We're going to do the exact same thing for our standard error of estimate. We're going to divide by degrees of freedom, but there's going to be one little tiny change. It's not that big a deal, but it's one thing to make a note of, is that our degrees of freedom is going to be n minus 2 rather than n minus 1. So this is because with a standard deviation, recall that when we calculate a mean for a variable, we lose the degree of freedom. And so when we calculated the mean for y, we lost a degree of freedom. But for the standard error of estimate, for our formula, and if you go back and look at our regression formulas, we need to calculate both the mean of y and the mean of x to get predicted values. So in the process of doing all our calculating here, we've actually calculated a mean for both x and y. We've calculated two different means, and so we've lost 2 degrees of freedom. So one little difference here is that the degrees of freedom for a variance is going to be n minus 1. For calculating the standard error of estimate, our degrees of freedom are n minus 2. So otherwise, everything's just identical here. We take our sum of squares divided by degrees of freedom to get our variance, or take our sum of squared error divided by degrees of freedom to get what I'll call the mean squared error. And then the final step, I'll just take the square root, turn it back into unsquared values, because at this point we've been dealing with squared values of stuff, so we're going to unsquare everything, that is, take the square root. So take the square root of my variance, and I have a standard deviation. Take a square root of my mean squared error, and I have the standard error of estimate. And recall that the standard error of estimate, that tells us on average how far do people's observed scores deviate from their predicted values. What is the average mistake that we make if I use X to predict people's score on Y? How much mistake on average do I make using X to predict Y? How far do their observed values on average deviate from their predicted values? That's what the standard error of estimate tells us. So let's plug everything into our example here. We've already calculated our sum of squared error and determined that that was 380. Let's finish out and do the other steps. So I'll take 380 divided by our degrees of freedom. We had 8 people in our sample, so degrees of freedom n minus 2 is 6. So 380 divided by 6, I get 63.33. So that is our mean squared error. And then I'll simply take the square root of that to get my standard error of estimate. I get 7.96. So that is the standard error of estimate that tells me how far on average people deviate from their predictive values. So when I use the traumatic bunny incidence, when I say how many traumatic bunny incidents did you have and try to use that to predict anxiety, I'm usually off. That's almost 8 points. I'm usually off by almost 8 points when I use traumatic bunny incidents to try to predict people's anxiety, at least in this particular sample. That's what I get. And again, standard error of estimate is giving me some information about effect size because the better I predict, the smaller this value will be. And if my prediction gets worse, this will be a bigger value. So this gives me some information about how much mistake I'm making when I'm trying to use traumatic bunny incidents to predict anxiety. So let's review. We've been talking about ways to talk about effect size, or the descriptive question of what's the size of relation between X and Y. We saw how the slope, beta 1, is one way to answer that question, gives us some information about the relationship. I don't have on this slide here a correlation, but we could also talk about how the fact that the correlation R is also an indication of effect size. And then just now we were talking about how our standard error of estimate, the average deviation of the EIS, the errors for how far people deviate from their predicted values, that average size of that deviation is also giving us information about effect size. So both the betas and the standard error of estimate are ways of talking about effect size, or size or relationship between X and Y. But that's not all. As you can see here, I say, let's take this one step further. I've got more to talk about this. We can dive into this just a bit further and look at some other ways we can talk about effect size, building on what we've talked about up to this point. Primarily, I want to compare these two values. Here I have the sum of y minus y bar squared, which is the sum of the squares, and sum of y minus y hat squared, which is the sum of the squared error, some of the squared errors. There we go. So again, we have here this top one, y minus y bar, the total sum of squares, and then this bottom equation, sum of squared error. And the only difference is it y minus y bar or y minus y hat? Are we saying how far do people deviate from the mean, which is variance, or how far do people deviate from their predicted values, which is estimation error? And if we compare these two values, that will help give us further information that will address this descriptive questions in a way that will be very helpful to us later on. So let's compare these two values and see how that can tell us information about the descriptive question, the magnitude of association between X and Y. As we go, let's note how the error is going to be related to the strength of your slope. And here I have some scatter plots. These look like the correlation scatter plots that we saw before when we talked about correlations. Up in the upper left, I have here's a correlation of 1. In the bottom right, I have a correlation of 0. And note how when you have a perfect positive correlation, all the dots fall right exactly on that regression slope. And so there's no error. We predict everyone's score perfectly. Everyone's score falls perfectly on that slope. There's no error. And as the slope gets flatter and flatter, the dots spread out more and more. With each as the slope gets flatter and flatter, the correlation gets weaker and weaker, the slope gets flatter, the dots spread out further and further, which is showing you that you're getting more and more error. And so when you have a 0 correlation, you get the most error you can possibly get. And when you have a perfect positive correlation, you have 0 error. Here's another slide. This is just showing you the exact same thing, except for rather than going for a positive correlation, it's a negative correlation. So going from a correlation of 0 to a correlation of -1. Exact same thing. A perfect correlation, you have no error. A zero correlation, you have the most error you can possibly have. Now let's look at exactly how much error do you have if there's a zero correlation. So if there's no relationship between X and Y, say I want to predict how much you like cute bunny rabbits based on the size of your big toe. And so I have some kind of special big toe calipers and I measure the size. I guess I'm on kind of a toe kick here for this unit. I have some kind of calipers that measure the size of your big toe, and then I give you a questionnaire and measure how much you like bunny rabbits. Maybe it turns out that there's absolutely no relationship whatsoever between the size of your big toe and how much you like bunny rabbits. There'd be a zero correlation. And recall that if I want to predict, say how much you like bunny rabbits, maybe a scale from 5 to 35 or whatever, how much people like bunny rabbits on this scale, and I want to predict how much people like bunny rabbits, and I don't have any information, then my best prediction is simply to guess the mean for everybody. That goes back to our very first unit when we talked about standard deviations and means, and how the mean is a predicted value. If I don't have any information other than the mean for a sample, then my best bet, if I want to try to predict or guess people's scores, my best way to predict their scores is just to predict the mean for every single person. And so if I'm trying to use big toe size, if this is your toe size over here, if I'm trying to use your big toe size to predict how much you like bunny rabbits, and toe size has nothing to do with how much you like bunny rabbits, and so if the mean is, say, what's about 22, it looks like the mean is 22. So here's this person here had a big toe size of 2. I'm not sure what that is measured in, but a big toe size of 2. What do I predict that person, how much that person likes bunny rabbits? Well, I predict the mean, 22, because toe size has nothing to do with bunny rabbit liking, so I just predict the mean for everybody. Here is someone up here. This person had a toe size of 4. What do I predict for bunny rabbit liking? Well, I predict 22. The same thing. No matter what your big toe size is, I simply predict the same thing. I predict the mean of Y for every single person, because big toe size has nothing to do with how much you like bunny rabbits. So what that means is Y hat, your predicted score on Y, and Y bar, the mean of Y, are the same thing. That if there's no relationship between X and Y, if the correlation between X and Y is 0, then it means that the mean of Y and predicted Y are identical things. We simply predict the mean of Y for every single person, and therefore this equation right here, the sum of the squared errors, how far people deviate from predicted values, is identical to this one over here. The sum of the squares, how far people deviate from the mean. The sum of the squares, the sum of squared errors are identical things. Error variance equals total variance. Or the sum of the squared error equals the sum of the squares. If the correlation is 0, if there's no relation between X and Y, then this is true. The intercept becomes simply the mean. We have this intercept here is right at the mean of Y, and we simply predict Y for every single person. So we can look at it this way. So if we have a perfect positive correlation, the sum of the squared error will be 0. Everyone will fall exactly right on that predicted value. Everyone will fall exactly right on that slope. We'll make 0 error. We'll predict everyone's score perfectly if we have a perfect positive correlation, because that's what a perfect positive correlation means. If we have a 0 correlation, then the sum of our squared error will equal our total sum of squares. The sum of the squared error equals the total sum of squares if we have a 0 correlation. So that means that our sum of the squared errors is something that ranges between 0 if there's no correlation. It ranges between 0. So this 0 right up here, it ranges between 0. The sum of the squared errors ranges between 0 if we have a perfect positive correlation, and the total sums of squares if we have a 0 correlation. In other words, we have the same type of thing we had when I talked about correlations, and I talked about a covariance, and how a covariance is something that ranges in size. It can be bigger and smaller, and the size of the covariance is related to the strength of association between X and Y, and a covariance ranges between 0 and the absolute biggest it can be is the size of your averaged variance. And so to calculate a correlation, we said, what percent of your average variance is covariance? We took a covariance divided by, do a little division sign there, divided by average variance to get our correlation. Because we can compare the covariance to the variance to get an indication of effect size. We can actually do the same basic thing here, where I take my sum of squared error. Now this is the inverse thing. This, I guess, was a correlation. We're being kind of happy and optimistic, saying how big is the effect, and now we're being more pessimistic and negative, saying how bad is our effect, because error, the bigger the error, the worse we are at predicting the outcome variable y. The weaker the effect is, the bigger the error. So now we're being negative and saying, well, how bad is the effect? But the same basic principle applies, is that the sum of the squared error is something that ranges between 0 if there's no effect, and the biggest it can possibly be is equal to your total sum of squares. It ranges between 0 and your total sum of squares. So we could do the same type of thing to say, what's the strength of association, and say, well, what's the size of the error compared to how big it possibly can be, which is the total sum of squares. And we can do that. We can do that in just a moment. But before we do that, let's stop being quite so negative here, because error is a negative thing. It's talking about how bad the effect is, and I'm starting to get sad and depressed talking about all this error and how much mistake we're making in trying to predict people's scores. Is there a way we could be a little more optimistic and happy? And can we talk about rather than how much error we have, let's instead talk about how much we're explaining. So where error is a lack of the effect, what is the opposite of error? We'll call that explained variance, which I have up here, explained variance. So that, I think that we could talk about error or explained variance, but explained is kind of the flip side. Error is the bad stuff of how bad we're predicting. Explained is the good side. It's how good we're doing. And so with that, the next question is, well, is there a formula I can give you? If the total sum of squares is y minus y bar squared, error is y minus y hat squared, what is the formula for explained variance? And, as you might guess, I have a formula for you right here. Here is the formula for explained variance. It is the sum of y hat minus y bar squared. So note that we're saying our total variance is how far people deviate from the mean. And essentially what we're doing that is we're taking that total deviation, how far people deviate from the mean, and we're partitioning that into two parts. One part is how far your score deviates from the predicted value, and then we say, well, then how far does that predicted value deviate from the mean? So altogether, explained and error add up to total. And actually, as we're going to see, mathematically, this is where it will always work out that way, so that explained plus error do equal your total variance. Let's look at this equation and see what it is and what it's doing for us, and why is y hat minus y bar squared and summed up. Why is that explained variance? What is that doing? So here's what it looks like. I'm taking each person and I'm calculating their, I have the same scatter plot, and we're looking at how, what their score is, what their predicted score is. So for example, and I forget who it was that was, my button is being hard. There we go. So this person right here, the predicted score is right there on the red line, and the mean is the blue line. So y hat minus y bar is the size of the difference between the red line and the blue line. And it doesn't matter what your score is on y. So for example, here's actually, let me go to another slide here. So let's look at this one here. We'll come back to that slide in just a moment. So here's Gus. And Gus had a score of 8 on traumatic bunny incidents. He had 8 traumatic bunny incidents. His anxiety was a 35. But for getting predicted scores, we don't care about anxiety. It doesn't matter what his score was on Y. So given that he had a score of 8 on X, his predicted score was a 28.5. We saw that in our previous slides, that if we plug our regression formula in, we get a predicted score of 28.5. So if you have a score of 8 on X, your predicted score on Y is 28.5. And now we want to just say, what is the difference between predicted Y and Y hat? So go from the red line to the blue line. The difference between the red line and the blue line is 6 units. 28.5 minus 22.5 is 6. So there's 6 units of difference between observed and the mean of y. Notice there were 2 people that got scores of 9 on traumatic bunny incidents, that had a score of 9 on X. One of them had a score of 25 on Y, this person right here, and one had a score of 35 on Y, this person right here. But we don't care for calculating explained variance. We don't care what they got on Y. For this, we just want to know what do they get on X, and given their predicted score, so given if you had a score of 9 on X, regardless of what you have on Y, your predicted score is right here. It's about a 30. And so in both cases, the y hat minus y bar was 8 units. So it's 8 units for that person and 8 units for this person. They had different scores on y, but that doesn't matter. They both had the same score on x. They both had a score of 9 on x. And so for both people, they have the same predicted score. And because they have the same predicted score, y hat minus y bar is the same for both of them. That's why they both have scores of 8. So let's, I just went back to that previous slide, noting that our explained variance is predicted y minus y bar. And I just want to note that this is measuring slope steepness, that the length of these green lines is measuring how steep the slope is. If I had a flat slope, if the slope was just going like really flat like this, then those green lines would be very, very short. If I had a really steep slope, maybe something like this, then the green lines would be longer. So the steeper the slope, the longer those green lines. The flatter the slope, the shorter the lines. So this equation, y hat minus y bar, is an indicator of slope steepness. In other words, the steeper your slope, and a steeper slope goes with a stronger effect. Recall that the better x predicts y, the stronger the correlation between x and y, the slope gets steeper and steeper. And so the steeper the slope, the bigger the effect. And this equation, y hat minus y bar, is a measure of slope steepness. So let's go ahead and calculate that for our example. So I took each person. For each person, I took their predicted score, which our red line gives a predicted score, and subtracted from it the mean, the blue line. So it's these lengths of the green lines, starting with the red point, red line to the blue line, the length of the green line, and then I squared it. So I took that explained variance, squared it, and summed it up. So 64 plus 36 plus 36 and so forth, 64, 36, and so forth. I add it all together, I get a explained variance sum of squares of 320. So that's my explained variance sum of squares, 320. Now let's do the same thing. Note how explained variance is related to the steepness of the slope. I was just talking about that a moment ago. And so if we have a line that's really steep like this, then we're going to have how far each person deviates from that slope is going to be really big. They're going to have a lot of, and we'll have and in this case, everything is going to be explained, and we'll have zero error. Whereas if we have a zero correlation, then our slope is flat, and we have nothing's explained, and it's all error. So if we have a perfect correlation, we're going to say that everything's explained, and we have zero error, because we can predict people's scores perfectly. That means we've explained everything. If we have a zero correlation, it means we can't predict anyone's scores, and it will be all error, and nothing will be explained. Let's see exactly what happens when I have a perfect positive correlation between x and y to our explained variance. If I have a perfect positive correlation, note that that means that my y hat is the same as your observed y. What you actually got in y is what we predict, because that's what a perfect positive relationship means. It means there's a perfect correlation, which means that if I know your score on x, I can perfectly predict your score on y. So if there's a perfect relationship, if I can perfectly predict your score on y, given your score on x, then y hat is the same thing as what you actually got, your actual y. So if y hat and y are the same thing, then how far y hat deviates from y bar is the same thing as how far y deviates from y bar. In other words, if there's a perfect positive correlation, y hat and y, those are the exact same thing if I have a perfect positive correlation, because I can perfectly predict y given x when there's a perfect positive correlation. So that means that if there's a perfect relationship, the sum of the explained variance sums of squares, y hat minus y bar, is the same thing as the total sums of squares, y minus y bar. In other words, explained sums of squares equals total sums of squares if you have a perfect positive relationship. Actually, it'd also be true if you had a perfect negative relationship. It would come out the same as well. So if you have a perfect relationship between x and y, then your explained variance sums of squares will equal your total sums of squares. So let's put this together and see both with error variance sums of squares and explained variance sums of squares and see how they change going from a correlation of 1 to a correlation of 0. It's just the inverse of each other. So error is 0 when you have a perfect positive relationship, and it becomes equal to your total sums of squares when you have a 0 relationship. In contrast, your explained variance sums of squares equals your total sums of squares when there's a perfect positive relationship, and it becomes 0 when you have a 0 relationship. In other words, if you have a perfect positive correlation, your total variance, everything's explained, your total variance equals explained variance, everything's explained, and error is 0. If you have a 0 correlation, everything is error, and explained is 0. So putting it all together, then we can be negative or positive. So we can talk about out of the total sums of squares, what part is error? That's kind of the negative way to look at things. Or we can say out of the total sums of squares, what part is explained? And it turns out that error and explained are just the inverse of each other, so we can do it either way. And as we'll see in a moment, error plus explained will always equal total. So what we're doing here is we're actually partitioning our total sums of squares into two parts. One part of our total sum of squares is error, and one part is explained. So we can say out of our total sum of squares, what part is explained? If we want to be happy and positive and optimistic, we'll say what part of our total sums of squares is explained. Or if we want to be negative and sad and grumpy, we might say what part of our total sums of squares is error. So we can use error or explained. And in both cases, error or explained, these are things that range between 0 is the lowest value they can be, and the size of your total sum of squares is the biggest they can possibly be. So they can range between 0, the smallest they can be, and the total sum of squares is the biggest they can be. It's just inverse about when they're 0 and when they equal the total. The error is 0 when you have a perfect positive relationship, and it equals your total when you have a 0 relationship, when there's no correlation. Your explained variance equals 0 when you have a lack of relationship. When there's a 0 correlation, when there's no relationship, your explained variance equals 0. And when you have a perfect positive relationship, your explained variance equals your total sums of squares. So here's how it looks in our particular example here. We had a total sums of squares. When we calculated that, that was 700. That's the sum of squares, y minus y bar. That's that was the first step in calculating the standard deviation of y. Our sum of squares was 700. If you go way back to one of our previous slides, we calculated that. Our error sums of squares, we calculated that. We got 380. And our explained variance sums of squares was 320. And note that explained plus error, 320 plus 380, equals 700. Explained plus error equals total. And it will always come out that way. Explained plus error will always equal total. So again, we have partitioned the sum of squares. We've taken our total sum of squares and say there's two parts to our total sum of squares. One part is explained and one part is error. And we figured out what part is explained, 320, and what part is error, 380. And explained plus error always sums up to our total. So with that, we can say, well, what percent is explained and what percent is error? So, for example, if we wanted to be negative, we could say, what is our error sum of the squares divided by total? And we'd calculate that 54% is error. Or if we want to be positive, and by the way, we're going to, for the most part, focus on being positive. That's kind of the way people do these analyses. And so people usually, in fact, they almost never talk about the percent of variance that is error. They always talk about the percent that's explained. And so we're going to be focusing on that. And so percent of variance explained, which is the primary way we could talk about percent that's error. It's just the flip side. But we'll be positive, say what percent is explained. And we'll take explained variance divided by total. So in this case, we had 320. It was explained variance sums of squares. Our total variance sums of squares was 700. 320 divided by 700 gives us 0.46. Now, so that means we've explained 40% of the variance. And does that number look familiar? Can you remember way, way back when I calculated that correlation and squared it for this data set? What do we get? We calculated a correlation of 0.68 for this data set. If you go way back to that very first, when I first started this unit, we calculated our correlation 0.68, and then I squared that correlation and we got 0.46, and that's exactly what we get right here. And it turns out this will always be the case, and that answers that question I raised a long time ago of why do we call a squared correlation the percent of variance explained? It's because if you partition your variance into explained variance sums of squares and error variance sums of squares and total variance sums of squares and take explained divided by total to calculate the percent of variance explained, that percent explained will always, always, always be identical to what you get if you calculate a correlation, covariance divided by the product of your two standard deviations to get a correlation, and then you square your correlation. Oops, I went the wrong way. Here's a correlation. I should have circled there. Then square my correlation to get 0.46. That will always equal the percent of variance explained. And that's why we call a squared correlation the percent of variance explained. So essentially, I've given you two different ways we could get at the same exact value. We could get 0.46 by first calculating a correlation and squaring it. Or we could get the same value by partitioning our variance into explained variance sums of squares and total and taking explained divided by total to get percent explained, and they both give us the same result. And this is two different ways of talking about effect size. The correlation can talk about effect size, and actually a squared correlation or percent of variance explained is also something we can use to talk about effect size. Now, at the moment, this is looking kind of redundant about two different pathways, which maybe we've had fun trying to think of all the different ways we can arrive at the same number, or maybe not. I'm not sure either way. But at the moment, it is redundant. I've just shown you two different ways we can arrive at the same value. In future units, we're going to use the different pathways, the different procedures are going to do different things for us. So it's not going to remain redundant forever. For this point, this particular unit, these are two redundant procedures, but later on we're going to expand upon this, and we'll use the partitioning of the variance will do one thing for us, calculating correlations will do something different for us. So let's summarize all the ways we've answered this descriptive question. We're wanting to know what's the relationship between X and Y, what's the relationship between traumatic bunny incidents and someone's anxiety. We could simply calculate the beta weight, and we note that if we take that beta weight and based on standardized variables, a standardized beta, which is the beta you get if you turn everything to z-scores prior to analysis, is the same thing as a correlation, and the correlation is also another way to talk about the effect size. Or we could also talk about the relationship by saying what's the standard error of estimate, the average size of these E's, EIS, from our top equation, how far people deviate from their predicted values, the average size of those E's, standard error of estimate, is also a way to talk about the strength relationship between two variables. In other words, as a relationship gets stronger, the E's get smaller. As a relationship gets weaker, the E's get bigger. And we can build on that and partition our variance into error variance and explained variance sums of squares, and then take the explained variance sums of squares divided by the total to get the percent of variance explained. And it turns out that will equal your squared correlation. So these are all interrelated things at the moment. Like I said, in future units, we're going to use different, each of these procedures are going to do something different for us, but at the moment, they're all giving us the same basic information. And now that's covered everything through part 4b